right, welcome back. We'll switch gears now and we'll have the second lecture from Yuri.
All right, welcome back, everyone. So this is sort of a summary of the last time. These are not the slides. Well, these are the original slides from yesterday. I haven't updated them. So it's slides from maybe, more fast-paced presentation, right? If we do everything in slides. Nonetheless, last time we talked about the dipole description of dipole picture of deep inelastic scattering, and we wrote a formula relating the cross-section of virtual photon, say, nucleus or proton scattering in terms of the integral over the dipole sizes x perp. We have the dipole wave function squared, and then we have a dipole amplitude and also integrated over z, the longitudinal momentum fraction. In fact, this is all also presented on the board still. I asked the organizers not to erase it. So we had the dipole nucleon and nucleus cross section, which is twice the integral wave parameter of n, and then that object itself entered the expression for the cross section. Let me erase something here, just a refresher. So it's a little not terribly organized. So the cross section for gamma star k was an integral d to x perp over 4 pi integral over z, dz over z1 minus z. Z is the longitudinal momentum fraction of the virtual photon's momentum carried by the quark. Anti-quark carries the fraction 1 minus z. And then we had this cross section of a dipole scattering on the nucleus as a function of x perp and s. Right, so this is the formula we wrote, and that is the formula we wrote. If you plug in the cross section on the right into the expression on the left, you're going to get, if it actually works, yeah, you're going to get that formula over there, right? So essentially, once you know the wave function, Icon wave function, we talked about it somewhat briefly last time, but the point is it is known. So QCD interactions are in the dipole amplitude. Once you know the dipole amplitude, you know the cross section of gamma star B scattering, you know your structure functions, you know a lot of other things as well. So that was the upshot. And then we said, okay, very good. If all QCD interactions are in the dipole amplitude n, and this is a QCD school, let's try to do a QCD calculation. So we said, all right, if we have a nucleus with many nucleons, at the very lowest order, the interaction would be exchange of two gluons with one of the nucleons. We're looking at the forward scattering cross-section, so that nucleon has to remain a color singlet state, right? It comes in as a color singlet. It should come out as a color singlet. It's a forward scattering process. So we cannot exchange one gluon. Break the nucleons, it would introduce color and break the nucleon. If we exchange two gluons, of course, they could be in a color singlet state, and that interaction is legit. So, and we said, okay, but if we have many of those nucleons, any of the nucleons can interact. In fact, actually, there was a caveat that gluon exchanges are short-range exchanges, so only the nucleons along the path of the dipole can interact. And there's on the order of 8 to the 1/3 of them. So this is what the explicit calculation showed in the end. So this result here is this two dipole exchange contribution to the dipole amplitude n. We called it n lowest order. We had that the cross section due to those let's say two dipoles, two gluon exchange with the nucleon contribution to the dipole amplitude, right? So this cross section is a cross section for the scattering on a single nucleon. And then we introduce the nuclear profile function, which roughly scales as 8 to the 1/3 for a large nucleus. So it kind of counts the number of nucleons to give an impact parameter. It comes in with a factor of 1/2 for optical theorem reasons. And we got this expression for n. That scales, as we discussed here, as 8 to the 1/3 coming from this TOP times x perp squared and T of B is also dimension full, so it brings in a factor of lambda squared, some infrared cutoff in order of lambda QCD squared to make the dimension less. The amplitude n is dimensionless. So it scales as e to the 1/3 x curve squared lambda squared. And the question is, when does the amplitude get strong? When does it become of order 1? And it seems like if we plot it here as a function of x perp, which we did, it grows with x perp, kind of like a parabola with a long correction, but roughly a parabola, and it grows unchecked. So it will become of order 1 when x perp is of the order of 1 over lambda a to the negative 1/6. And this a to the negative 1/6 is important because when the nucleus is large enough, the problem that n becomes greater than 1, the problem occurs when the dipole size is still much smaller than 1 over lambda, right? If a is a large number, a to the 1/6 would be considered a large number, so a to the minus 1/6 is a small number. So this dipole size is still much smaller than the non-perturbative scale. So we still should have control over our calculation. This is not where non-perturbative physics comes in, right? Non-perturbative physics comes in somewhere out here when x perp is of the order of 1 over lambda, but the problem occurs before. So we should rightfully worry about it, right? And say, well, this is where the calculation is under control, but it makes no sense because n becomes greater than 1. Does anyone remember why n should be smaller than 1? What is the underlying reason?
It's the probability amplitude.
It's a scattering amplitude. It's not a probability. Yes. Huh? The Black disk limit, right? So unitarity implies the Black disk limit n should be less than or equal to 1. Do you guys want me to give you a brief reasoning? Yes. Is it okay if I use slides or yes? Okay. Let's do the slides because I don't want to spend way too much time on it. So let me. And those of you who joined us last night for discussion kind of saw parts of this argument. So this is a very, very stickman discussion of unitarity, but just to convey the message, maybe without all the gory calculational details, this is kind of the level of maybe quantum mechanics, if you wish. So you start by saying, suppose you have some scattering process, you have the initial state and final state, and they're related by the S matrix, right? The S matrix operator is with a head, is like a time evolution operator, takes the initial state, converts it into the final state. In scattering theory, what we do, we write this final state as the initial state plus a correction, which will be S hat minus 1 acting on the initial state, right? So this is the scattered part of the state. The cross section is the scattered part, the total cross section, sorry, it's just this scattered part of the state squared, proportional to that. And remembering that S is a unitary operator, right? S matrix is unitary, so S as dagger is 1. If we multiply S minus 1 by S dagger minus 1, we're going to get this. 2 minus S star, where S is kind of sandwiched between initial and final state, right? Does this sort of make sense? Oh, by the way, I forgot to mention homework. If you want to do homework, there is homework. It's completely optional. I'm not going to grade it. Maybe Alexei will grade it, but not me. Being volunteered. And you know, if you like it, you can read more or do more of the problems in the book. So what I was saying is, if you have S dagger minus 1 times S minus 1, right? So you're squaring this operator here, you're going to get S dagger S plus 1 minus S dagger. S dagger S by unitarity is 1, so you're going to get 2 minus S dagger, right? At the operator level, and then if you sandwich that, between the Bryan cat initial states, you're going to get just S and S star. Okay. So far so good. Yeah. Button. If you want an elastic cross section, elastic is just the probability that the scatter state is the same as the incoming state. So we just take the overlap of the scatter state and the incoming state, and we square it. and that's just 1 minus S without the head, the matrix element of S hat sandwiched between psi initial states, absolute value squared. And finally, inelastic cross-section can be obtained by noticing that the total cross-section is the inelastic plus elastic, and we already found the total cross-section on the previous slide, and sigma elastic is up here. So sigma inelastic we can just obtain by subtracting sigma elastic out of sigma total. Okay, so when dust settles, and I introduce, instead of this proportionality signs, I introduce a little bit more accurate counting, which is just integrals over impact parameters. We can write the total cross-section as twice integral d to b 1 minus the real part of S, right? This is because this factor here can be written as 2 times 1 minus the real part of the S matrix. That's the total cross-section. Elastic cross-section is absolute value of 1 minus S squared. S is now a function of the impact parameter, so we integrate over impact parameters, and sigma inelastic is given here. So these are useful formulas in and of their own right, and they're very handy in many different situations. Now, what about unitarity limit? Well, you do the following trick. You say S is a unitary operator, so S's dagger is 1. Matrix element of S's dagger is also 1, right? Because S's dagger is 1, matrix element of a unit operator is still 1. On the other hand, we do the standard quantum mechanical trick and insert a complete set of states X between S and S dagger, right? So we insert a set of states X with sum over X, and this is a cat and this is a bra X states. It's a complete set. It includes the initial state as well. And that means that if X is the initial state, we get absolute value of S squared, but X could be other things, so we get an inequality, right? The expression on the left is equal to S squared if we only insert psi initial, but we need to insert all the other states. And for each of those states, we have a matrix element squared, so we have other positive terms in the sum, which apart from this S squared, therefore we have an inequality. The sum is greater than or equal to the absolute value of S squared. And so we see that 1 is greater than or equal to absolute value of S. That means S should be less than or equal to 1. So that's a true unitarity bound on the S matrix, that the matrix element of the S matrix should be less than or equal to 1 in absolute value. Okay, so what does it mean? If we're looking at the total cross-section, in fact, the largest real part of S can be, if absolute value, the largest 1 minus real part of S can be, if S in absolute value is less than or equal to 1, is 2, right? If S is negative 1, then 1 minus negative 1 is 2, which is bigger than, say when S matrix is 1, then 1 minus 1 is 0. And everything in between on the real axis, right, between 0 and 1, you'll get something smaller than 2. So the real bound is actually, you get a factor of 2 here with a factor of 2 out in front. You get 4 integral over all impact parameters. If you're scattering on a sphere, say of radius r, integral over impact parameters will give you pi r squared. So you get 4 pi r squared. So this is the really strong unitarity bound for the cross section. But the problem is that when the S matrix is negative 1, your inelastic cross section is 0, right? Inelastic cross section is 1 minus absolute value of S squared. If S is negative 1, 1 minus 1 is 0. And elastic cross section then is actually equal to the total cross section. So this unitarity bound is all very well, but it's realized actually in a very low energy scattering. If you talk to maybe nuclear reaction people and maybe the ones more senior that remember the old days, they would tell you, okay, this is a true bound, and that's what they have. They have those nucleons scattering on each other without breaking. Everything is elastic, but the cross section is bounded by 4 pi r squared. Okay, now this is not what happens in high energy scattering. In high energy scattering, the argument goes roughly like this. You can demand that in high energy scattering, we're more likely to have inelastic scattering than elastic scattering. If we demand that and go back to these formulas, a few minutes of algebra. Maybe I should leave it as an exercise, additional homework exercise. So if you look at these formulas here and demand that sigma inelastic is greater than sigma elastic, and ask yourself what it means for S, you will see that it means that real part of S should be non-negative. And in that range, the largest your cross-section can be is achieved by S matrix being 0. Then 1 minus 0 is 1. So we get 2 pi r squared, the total cross-section. And this is known as the black disk limit. Okay. In that regime, when S matrix is 0, S elastic and S inelastic are equal to each other and equal to pi r squared. And each of them are a half of the total cross-section. So as opposed to that low energy limit where everything was elastic, inelastic cross-section was 0, elastic cross-section was equal to total cross-section. Here in the black disk limit, inelastic and elastic scattering happen on equal footing. They each come with the same cross-section of pi r squared, and their sum gives us 2 pi r squared, which is the total cross-section. This is still not a trivial result, right? We're talking about very, very high energy scattering when things are breaking up left and right. But the point is the cross-section, the elastic cross-section is still half of the total cross-section. Okay. And in terms of N, remember, well, no, you don't remember, but one can argue that N is the imaginary part of the T matrix. So, I have a small formula here. S is 1 plus IT. Maybe I should write it someplace else. All right, let me use a different color to make it maybe more visible. So S matrix, remember, is a 1 plus I times the T matrix. And if N is imaginary part of the T matrix, and I tell you without proving, and you have to trust me, that at high energy scattering, the scattering amplitudes that dominate are mainly imaginary. We can neglect the real part of the T matrix. Then this is going to be equal to 1 minus N. And I guess I'm being sloppy, so let's remove the operator notation and think of these S and T as forward matrix elements of the S matrix. So when I say that my N is approaching 1, like on the board there, right? So when N approaches 1, that means S matrix approaches 0, which is exactly the black disk limit we just talked about. Or another way of putting it, one can rewrite those cross sections, total elastic and inelastic, in terms of this N instead of S, and get these formulas here. So the total cross section is 2 integral d2bn. This is exactly what we have all the way on the far left, right over here for the dipole. It's true for any type of scattering projectile dipole or whatever you have. If n is a dipole amplitude, then of course it's a dipole cross section. Elastic cross section is n squared. This is inelastic cross section. The black disk limit is realized when n is equal to 1, and the total cross section becomes 2 pi r squared. Okay, I don't remember if I have a slide on that. No. But the point is that remember, I just said real part of S is greater than or equal to 0. That means n cannot exceed 1. If n exceeds 1, your S matrix becomes negative, so you violate unitarianism. Okay, you violate the black disk. Okay, so that was a detour on a black disk. Any questions about this? Bottom line is we don't want n to exceed 1. This is a bound we don't want to violate. And our formalism in the meantime seems to violate this bound, so we have to do something about it. Okay, any questions? All right, so then let me ask, what do you think we should do? How do we fix this problem? We set up a formalism. You know, it seems to be all good, except that, you know, we violate unitarianism. So obviously it's not all good.
There's something missing.
Yeah, so what is missing? Multiple scattering. If interaction with one nucleon happens, becomes very strong, right? And it's not probability, but it's sort of like probability of interaction becomes high, then, why stop? Why interact with only one nucleon and have other nucleons be spectators? Other nucleons can also interact as well, and the interaction could be just as strong. So this is avenue we're gonna pursue next. All right. I have to erase this thing on the right-hand side, even though I drew it, but I have to clean this up. And you've seen these formulas already today and also on the slides. So I think I can erase it at least. So by the way, you see I did mention briefly that unitarity meant n should be less than 1. Okay. So so the next maybe subtopic is Reboff, Glauber, Miller. So our goal is now to try to account for a dipole scattering on the nucleus, interacting with many different nucleons, not just with one of them. The exchange with each nucleon would be a two-gluon exchange. As we discussed last time, remember those are Glauber gluons in the SCAT framework. Those are instantaneous gluons. So you can they're kind of localized. If the dipole is moving in the light connects minus direction, all these interactions are instantaneous, and all the nucleons are kind of separated apart from each other in the x minus direction. So let me maybe quickly sketch here the space-time representation. I remember a dipole is moving to the left along the x minus axis. Our nucleus is moving to the right along the x plus axis. So this is our nucleus. And the dipole goes through, so let's say each line is a nucleon. As the dipole encounters a given nucleon, it interacts with it by exchanging a pair of gluons. Again, it should be two gluons with each nucleon because it's the minimum number of gluons you can exchange with the nucleon to leave a color singlet in the final state. Okay, so that's the picture, and the question is how to, how to sum up these interactions. Well, the way you do it is you say, okay, we have interactions happen at different times, right? So the first nucleon interacts at time x1 minus, the second nucleon interacts at time x2 minus. Using notation in my notes, the mth nucleon interacts at time xm minus. Not n, but m, because n is already taken for the dipole empties. Okay, so we have and we have a nucleus. Let's say it has a diameter of twice its radius r. 2r is the diameter of the nucleus for simplicity, and then we will have something like an integral dx1 minus from negative r to r, the integral dx2 minus from x1 minus to r, right? These are ordered, right? We don't want to double count. So x2 minus happens after x1 minus. So the integrals, the limits of the integrals are nested, right? The integral over dx3 minus goes from x2 minus to r all the way to the integral of minus 1 minus to r. And then each of these interactions really just brings in a factor of 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 actually negative n. Okay. Why negative? Just think for a second. So right now we are kind of including. Imagine that we're calculating the S matrix. The S matrix, as opposed to T matrix, includes the one, right? S matrix is 1 plus IT, so it includes the non-interaction keys. And the S matrix is equal to 1 minus n. So at the leading order, we have a leading order S matrix, which would be the non-interaction term minus this NLO, the two gluon exchange piece. And so at the linear order, we have one iteration of negative n. So the minus sign is because of the sign difference between the S matrix and this amplitude n. So what we have, what we're going to have is we are going to have essentially, well, maybe I'm being a little floppy. So let's try to be actually, let me restore this formula. Let me just try to be a little bit more careful. So let's say I have a cross section, d sigma d2b, right, which is 1/2 T of b sigma QQ bar n. But remember, T of b is an integral over this density, nucleon density over the longitudinal momentum. Now I wrote the integrals of the longitudinal momentum explicitly, so I cannot just jump to n. I was trying to cut some corners and I have been sloppy. So what really happens is I have a density of the nucleons at a given impact parameter at, say, position x1 minus. I have a density of the nucleons at the same impact parameter position x2 minus all the way to the density of the nucleons. Okay, some things I can erase here, I better do. At position xm minus. And then the remaining part, if I'm calculating n, right, n is 1/2 of d sigma. So if I invert this formula, I can sort of say that n is 1/2 d sigma d2b, right? But if I integrate right. So we would no, that's so good. And then I have the minus sign I discussed. So we'll have minus 1/2 d sigma QQ bar nucleon d2b to the power m. Right? We have this cross section come in with every interaction. It depends on the impact parameter. It doesn't depend on the x minus variable. And then if you buy all this, and let me separate it, the nested integral, right? The nested integral we know how to do. These densities are not operators, right? They're just numbers. So we can just write the nested integral as 1 over n factorial integral from minus r dx minus rho of b term x minus to the nth power times this minus 1/2 d sigma QQ bar n d2b to the mth power.
It should not be independent, right?
This should be what?
It should be independent of B.
No, it's B. What should be independent of?
And this dipole amplitude.
Oh no, the dipole amplitude is M is B dependent. Let me just pause for a second. Yeah, no, this is so fun. Yeah. Okay. So this is for M scatterings, and then we have to sum over all M from 0 to infinity. That's our S matrix. So we insert here a sum over M from 0 to infinity. And lo and behold, it exponentiates, right? So we're gonna, the answer is an exponential of negative 1/2 d sigma q bar and d2b times this integral right here, which actually is just a factor of T of B, the nuclear profile function. Okay, so that's it, right? That's the result for the S matrix of a dipole of size x perp, at the impact parameter B perp, and maybe some center of mass energy scattering on a nucleus like this. Okay. So if this all makes sense, if it doesn't make sense, just trust me. Well, let's say from general arguments, you could say if you have many independent scatterings, if they're completely independent, then their sum is just an exponential of a single scattering, right? Just because you have combinatoric factors, right? They're all identical and independent of each other. Okay, so if, let me leave that formula over there. If we put it all together, the S matrix becomes let me leave the unitarity limit as well. So S matrix of X perp, B perp, and central mass energy S is just e to the minus, bless you, 1/2 T of B perp, D sigma QQ bar, nucleon D2B. And we look at this expression and we realize that this is just e to the negative n leading order of X perp, B perp, and S. Or looking at this formula, we have e to the minus 1/2 pi alpha S squared CF over NC, X perp squared T of B perp log 1 over X perp log. Okay, so this is the S matrix for the scattering. The dipole amplitude M corresponding to this S matrix. This one we just obtained by taking 1 minus S, right? Remember the formula, S is 1 minus N, therefore N is 1 minus S. So we have 1 minus e to the minus, let's keep all the factors, 1/2 pi alpha S squared CF over NC, X perp squared, T of B perp log 1 over X perp log. Okay, you say, great, you got some lengthy formula. What does it mean for us? Huh? Yeah.
If you write D sigma D2B,
Yeah.
that is also depends upon impact parameter.
How do we get? So what is the problem?
So the first expression that you have wrote here.
Oh, the starting line.
No, that.
Oh, that one. Yeah.
Yeah. So if you simply put the expression for D sigma D2B later, there will be two things from.
We're using dimensions on work. Okay, just one second.
Yeah.
Okay, yeah. I think the right way to go is to say that I just have a cross section of a dipole scattering on a nucleon. It is dependent on the, so it's kind of funny because you think of a large nucleus, right, made of nucleons. And you have the dipole scattering. You have the impact parameter with respect to the center of the nucleus, but you integrate over positions of a nucleon on that shorter distances of the order of a Fermi, and that what goes into that cross section. So you have a kind of coarse graining, right? The small fluctuations, the positions of nucleons are integrated out. The big impact parameter dependence is included. Yes, sorry. So that's why one doesn't have a differential cross section. No wonder I was kind of worried that my notes show me something else. If we do it this way, right, then indeed I can just copy this formula, right? That's what you were worried about, that the formula was, yeah. Okay, and dimensions also were not working because T of B has dimensions of mass squared and sigma QQ bar M has dimensions of A. Okay, my bad. Yeah.
So the end picture has allowed us to take into account all these interactions with multiple interactions within nucleus. But what about multiple or higher order gluon exchanges with one single nucleon?
So the question,
Gluon 6.
right? So you're asking why not include extra gluons here? Okay, there is a summation parameter. So if you really want to, you can include those. Requires some work, but people have tried and succeeded in some cases. There is a summation parameter here, which tells me that this is a leading result which we have derived, and high order gluons are really high order corrections. So multiple gluon exchanges are high order corrections, but it's good to stress. So there is summation parameter. Remember, T of B scales as a to the 1/3, right? Because the dipole encounters on the order of a to the 1/3 nucleons at the given impact parameter. And then we have alpha s squared coming from the two gluon exchange with each nucleon, right? So we have alpha s squared, we have a to the 1/3. So the summation parameter is alpha s squared a to the 1/3. And we kind of assume that it's order 1. Alpha s we assume to be small. It's a conservative calculation. Atomic number E we assume to be very large. Alpha s squared a to the 1/3 we assume to be order 1. So from that standpoint, what you're asking about, those extra gluons, right? So specifically a 4-gluon exchange, right? That would bring in the power of alpha s to the 4th per 1 nucleon. So it's the same a to the 1/3, right? We have exchanged 4 gluons with the first nucleon, second nucleon, etc. A to the 1/3. So this is alpha s squared times alpha s squared a to the 1/3, right? If alpha squared a to the 1/3 is order 1, the whole thing is order alpha s squared, so that's a high order correction. You may have other processes which specifically are sensitive to something beyond those two gluon exchanges, and there you may need higher order, high number of gluon exchanges. For instance, there's another one which requires a 3-gluon exchange at least with 1 nucleon. But other one, it's a certain symmetry requirement on the dipole amplitude that we're not imposing here because we're looking at just total cross section without any symmetry constraints. So in our case, high order exchanges are just higher powers of all things. They can be included, but they're not part of the leading order approximation. Okay. Yeah.
There you're defining the N below as 1,
Yeah. N leading order. Yes.
and then you're putting there in the e to the minus N LO.
So this was the leading order S matrix, which includes non-interacting piece and a single two gluon exchange. Just one exchange like that. Forget about extra gluons. But there on the left, we sum all the many two gluon exchanges.
Yeah, the thing is that you are like obtaining an N in the final step.
Yes.
And I don't know what's the relation between that N and this N.
Oh, this N is 1 minus S. S is e to the minus N LO. So the relation is N is 1 minus e to the minus N LO. So if you expand it to the leading order, n is equal to NLO, but then you have higher order corrections. There's no pun here about next to leading order. This is n leading order. Okay, so NLO is just two gluon exchange. It's just a statement that if we sum all the gluon exchanges, we just exponentiate a single two gluon exchange. In this GGM picture. Okay. Now, moment of truth. What is it good for? So let's try sketching n dipole amplitude as a function of x perp squared. When x perp is small, the exponent goes to 0, 1 minus exponential goes to 0, so n again goes to 0. And that's again just a statement that when NLO is small, n is equal to NLO. Okay, and this is, as I mentioned before, last time is color transparency. The statement that if your dipole is zero size, the colors of quark and anti-quark screen each other and the interaction goes to 0. It's still preserved, right? It was valid yesterday for a two gluon exchange. It's still preserved if we include additional gluon exchanges. But as x perp goes large, right, the exponent grows, if I forget about the minus sign, but because of the minus sign, the exponential goes down to 0 as x perp increases. And the overall expression for the dipole amplitude m approaches 1. It doesn't violate unitarity anymore. It doesn't grow above 1. What happens, right, it starts out growing and then it sort of turns over and asymptotically approaches 1. Of course, when x perp becomes really of the order of 1 over lambda, right, the log may change sign eventually, and that things would happen, but that's really a non-perturbative region, right? So we don't go up to 1 over lambda. We see the turnover and preservation of unitarity for dipole sizes much smaller than 1 over lambda. Okay, so so black this limit is preserved. Unitarity is not violated. Those multiple rescatterings came in and saved the day. We're not violating unitarity. Yeah.
I have a more conceptual, not
That's fine.
higher level. So,
Right.
okay, so no, let me, so you followed the math, did all these cool things, and at one point, did people say, okay, what does this actually mean? Like, at what point did someone say, I think this is leading to gluon saturation? Because I feel like sometimes it's a theory. People can do all sorts of like really cool whistles and belts, and then I'm like, okay, but what can I then do?
Right.
For the experiment?
So
I know
well,
this is the gluon saturation, but at
right.
what point did someone say, I think this is that? Or,
how did people connect it to
yeah,
saturation?
yeah.
So let me answer at this maybe physical hand waving level. So what we see is that when interactions become very strong, you can have multiple interactions. And that's what preserves unitarity. So if one interaction is highly likely, then two interactions are also highly likely, and three interactions, etc. So you can have multiple interactions. You can think of this in a different way. You can think of it as the density of gluons in the nucleus being much larger than the density of the gluons in the proton. So, and you can think of it as saturation in the sense that different gluons kind of find each other and find a way to interact with each other. How can I maybe reason a little better? Yeah, I think maybe at a very, very bird's eye view level, if you have multiple interactions, there's no reason for a gluon in a gluon distribution inside the nucleus to be alone, right? If multiple interactions are all the game, different gluons in the nucleus can talk to each other, can interact with each other. And that's really the essence of situation. Is it
Yeah, that's
good
fair,
enough?
that's fair. That's a
You
good
wanted
point.
a broad answer.
No, that's fair. I asked the broad
That's what
question.
I'm trying to do. Okay. Right. So unitarity is preserved, and the transition, this turnover here, happens at the scale where the exponent is order 1, right? So we define saturation scale. I have to erase something. We define a saturation scale as follows. So QS squared is defined to be 4 pi alpha S squared CF over NC, C of B curve. Okay, just pause a second till let me pause a second to get my factors of 2 right. Both important. Yeah, okay. So for whatever reason, I have these guys squared here in my notes. So if you try to keep, so the argument of the log is squaring. Trying to keep track of all the factors of 2, which obviously I'm failing to do. If you insert that, then with this definition, so this is the so-called saturation scale in this quasi-classical picture. Then the dipole amplitude is E1 minus e to the minus 1/4 x curve squared qs squared. QS squared, by the way, depends on B curve. So it's input parameter dependent, and then we get the log of 1 over x curve lambda. I could dig out the factor of 2, but I think in the interest of time, I think there are more important things to discuss the factors of 2. So I apologize for dropping it somewhere, but worse things have happened. We see that the exponent becomes large. Forget about the log, forget about the quarter. The exponent becomes large when x curve is of the order of 1 over QS of B curve, right? So transition here happens at x curve of the order of 1 over QS. So transition happens around the saturation scale when the dipole size reaches the inverse saturation scale. That's when the interactions become strong. Notice that in our power counting, the saturation scale scales as alpha S squared, maybe some scale lambda squared, a non-perturbative scale associated with T of B times e to the 1/3. So saturation scale certainly gets very large could get very large for very large nucleus. So we may be in the perturbative region still where this turnover happens. So this is perturbative. Okay, and that's the point. This is an example of a saturation behavior in this GGM picture. Okay, unitarity is preserved because of saturation. Okay, any questions? Yeah.
If QS depends upon B, B is not an observable, right? So QS,
B is not a direct observable, but it is somewhat inferable from the experiment. For instance, in heavy ion collisions, like the diagonal multiplicity, and they pin their events by multiplicity, and then they have do some Glauber modeling. Similar. Central impact parameters and low multiplicity effects, for instance, with peripheral impact parameters. And they get so good, I think that they go by like 10% beams. So even fewer. I think the very central beam goes from 0 sometimes to 3%, if I remember. So while you cannot exactly measure B, in some cases you can measure combine it. You can at least measure ranges of parameter. It's a little harder, probably a lot harder to do in electron, proton, or electron-ion collisions, just because multiplicity is not that big. If you look at elastic scattering, right, this sigma dt, where T Mandelstam variable is some momentum transfer, approximately, let's say, small x is negative momentum transfer squared. This delta curve is a Fourier conjugated to B curve, and people doing GPD studies know this very well. So if you can get delta curve dependence, in principle, you can take square root of this thing, Fourier transform it, and get B perp dependence. So B perp is almost not zero. But yeah, it's not like one theorist long time ago I heard said, well, you just move the beam a little bit.
Yeah.
That's your B perp.
Sorry.
No, it was meant as a joke. No, we don't. Yeah, I mean, you guys, the experimentalists, don't move the beam. Okay. All right. So, yeah. So,
Formula of N, where is S?
that's a very good question. That's what I was going to ask next. There's no S on the right hand side. It's completely energy independent. I've been dragging this energy dependence along, but I've been kind of doing it in vain, it seems, right? There's no energy dependence here. The saturation scale doesn't depend on energy. So where is the energy dependence? Why do I have this S in the argument? Well, that's the next topic in the remaining whatever amount of time we have. I'm sure plenty. So energy dependence comes in through something called small x evolution, and I'm just gonna sketch the main points of it, given our ample time, the ample time that we have. So small x evolution. So exactly the question. So the big question is, well, let me write it here on the left. Where is the energy dependence? Well, obviously nowhere in this picture so far. But then you ask yourself a question. So we have a dipole, right? The photon fluctuates into QQ bar pair, which then goes and interacts with all those multiple rescatterings. But I told you, right, and I had the picture here, the space-time picture, all this interaction is localized. So all this interaction is fast. Interaction happens fast, so I can kind of redraw it as just you know, a shock wave. Remember we briefly discussed shock wave last time. So just some sort of a quick interaction with the nucleus, even though it includes all these many different rescatterings. So it seems like our picture is very kind of barren, right? If you look at it from this angle, you just have a quark antiquark pair which propagate alone for a long time until they find the proton or nucleus, interact with it, and then they go off on their merry way, not interacting for a while long. Well, this is fine in this multiple rescattering 3M picture where you some powers of this alpha s squared a to the 1/3. But you can ask a question: why does the quark and antiquark? Why do they have to be alone? Why can't they have a gluon fly along with them and do something like this? Quark antiquark pair emits a gluon. Then a system of quark, gluon, and antiquark interacts with the target, and then goes off and reabsorbs the gluon. This way, you can have other diagrams like that, etc. Many other single gluon corrections. Now, if you ask, well, why stop at one gluon? There's no reason, right? In principle, you can draw diagrams with more than one gluon. You can have diagrams with two gluons, for instance, something like this. So quark and antiquark produce two more gluons in the system of quark. Two gluons and antiquark interact with the nucleus and then recombine back, and etc. Now, you could say, oh, but you know, if you're careful about your power counting, you know that each gluon costs you a power of alpha s. Alpha s is assumed to be small. These are all high order corrections. Very well, indeed. Each of these gluons comes in with the power of alpha s. So this diagram brings in the power of alpha s. But my point is that you also have to integrate over the phase space of this gluon, right? You emit a gluon, you integrate over the phase space, and this phase space integral will give you a log of center of mass energy, right? Exactly as center of mass energy that we are looking for. So again, this becomes your summation parameter to make it the dimensions right, you have some infrared cutoff, right? So if I really want to be careful, it's going to be log of S over lambda squared. Again, the power counting is such that alpha S is very small, log of energy is very large, and we assume that this product alpha log of energy is order 1, and that's a resummation parameter that we would like to resum. So we want to resum all orders of these parameters. Okay. Now, if I'm so ambitious that I want to resum all orders, I shouldn't stop at 2 gluons, right? I should include 3 gluons, 4 gluons, etc. So my general diagram would be some sort of monstrosity with some complicated gluon cascade with even virtual corrections and this and that, and this whole thing interacting with a shock wave and then recombining back. Okay, so I need to resum a gluon cascade. So I need to sum up the cascade of gluons. Okay. Now, we don't need to sum up the cascade exactly. We just need to extract the powers of this parameter alpha log of energy. Now, nonetheless, it looks pretty scary, right? You have some general cascade of gluons that you have to sum. Now, you may ask why my gluons are not splitting into quark-antiquark pairs. My answer will be that it will not bring us a log of energy. So this will be outside of the summation of these parameters. So we only need to deal with the gluon cascade. We should not worry about quark-antiquark pairs in this cascade. We also, again, you have to trust me, there are no emissions of gluon from inside the shock wave. The gluons are emitted either to the left of this shock wave interaction or to the right. They are not emitted inside the shock wave at this high energy limit, at this resummation of this leading load parameter. So how do we resum this scary cascade of gluons? So I have to erase something. Maybe I'll have to erase all this. So the way to do it is you can work with operators and get operator expressions in terms of Wilson lines, and that's fine. But I'm just gonna give you maybe a diagrammatic representation of how this cascade resummation works. And to do that, you take the large and C limit. So to resum the cascade, take a large and C limit. So NC goes large, alpha S and C is kept constant. This is a two-fudge and C limit, and we discussed with some of you last night about this. So what happens then is if you take a diagram, let's take a single gluon emission. We have a quark and antiquark. We have a single gluon that interacts with the shock. What happens to this diagram in the Lagrange C limit? Well, the way Lagrange C limit works, remember your group theory, right? If you have a fundamental representation of SU3, you have 3, say, cross anti-fundamental 3 bar. This is equal to, does anyone remember?
8 plus 1.
8 plus 1 or 1 plus 8. Right? 3 times 3 is 1 plus 8. It does work. If you remember, I want to take Lagrange C. So my 3 becomes a variable. So if it's SU and C, the statement is NC times NC bar is equal to 1 plus what? NC squared minus 1, right? Again, algebra works. NC squared minus 1 plus 1 is equal to NC squared. If your NC is large, right? So if NC is large, this is approximately just NC squared minus 1, right? That's a much bigger representation than a singlet. So in other words, if I have a quark and anti-quark at large NC, most of the time they're in a joint representation. I almost said octet, but it's not octet, right? Because NC is large. It's a joint representation, not in a singlet. Okay, so this is a joint, which is a representation of the gluon. Yeah. So that means that the gluon on the right hand side, I have a gluon. Yeah. That's this guy. At large NC, you can write it as two lines, a quark and an anti-quark lines. Right? One is NC, that's a quark. Another one is NC bar, that's the anti-quark. Okay. Does this make sense? So the point is that if you want to understand the color structure of a gluon at large NC, you can replace it by quark and anti-quark lines, which with different colors, right? So that altogether it's a joint. It's not a color singlet. This is not a dipole. This is not a dipole QQ bar pair. This is a quark and anti-quark in a joint representation. So in other words, if this guy is red, this is anti-green, for instance, right? They're different colors all the time, most of them, 99.9%. So that means this diagram, in this diagram, I have to replace my gluon by a double line as well, like this. And this is my shockwave now. So let's see what happens. I have a quark line here and an anti-quark line here. And the quark line continues down here like this. And maybe let me use a different color. So that would be a red quark line. And the red color flows like this. Whereas out here, I have a quark line continuing this way. It flows, color flows back this way. So I have a blue, I have a blue quark line here. Okay, so I started with a quark anti-quark dipole, which initially was a red quark anti-quark dipole. After I emitted the gluon, my original dipole split into two dipoles. One is made out of the original quark line and the anti-quark line of the gluon. That's the blue dipole right here. So these guys together form a dipole. Again, the dipole is not made by the quark and anti-quark lines on the gluon. It's an anti-quark line on the gluon and the original quark line form a new dipole, not the original parent dipole. Small x, we refer to this guy as a daughter dipole. And we still have a red dipole, except it has a different size as well. It's made out of the quark line of the gluon and the original anti-quark line here. So this here is another dipole. Okay, does this make sense? So your original dipole splits into two dipoles, and that's great because your degrees of freedom remain the same. You started with a dipole, you end up with a dipole, with two dipoles. Okay, so you can write a self-consistent evolution equation. Namely, let's think of the S matrix. So suppose I have my original dipole with quark positioned at x1, the anti-quark position at x0, some transverse positions. Remember, we're working in the transverse position space and longitudinal momentum space. And suppose all the subsequent emissions and the interaction with a proton or nucleus, we're going to denote by some globe. And it's going to be the S matrix. And I'm going to use it slightly different notation. So far, I had the dipole size and the impact parameter. Sometimes it's also, if you have a dipole made out of quark and anti-quark, one is at x1, one is at x0. It's convenient to write the dipole amplitude as a function of position of the quark, position of the anti-quark, and energy. So it's a different linear combination, right? X perp was the size of the dipole. B perp was the impact parameter with respect to some fixed position maybe of the target. So you can choose different bases. You can work with X per B per, or you can work with X1 and X0. The X1 and X0 notation is more convenient because you know exactly which lines you're talking about. So I'm going to switch the notation. So my S matrix here will depend on positions X1 and X0 and energy, which is little s. And then I say, okay, so if I change energy, I do one step of evolution. So the evolution will be in the log of energy. That requires, to prove this requires a calculation. I have no time, ample time as I have no time for. Anyway, so, but as I change the energy, what happens to this S matrix? If I change the energy, I have more phase space, I can emit an extra gluon. The gluon can be emitted in many different ways, right? I tried drawing some diagram on the far right, some of the diagrams on the far right. This is just one diagram. You can have a diagonal the other way. You can have a quark emitted this way. And that way, the point is all those quarks, all these diagrams where the gluon goes through the shock wave, they split the original dipole into two dipoles. So I'm going to summarize it like this. You have some sort of a gluon line, a double line, whichever way it connects to quark line 1 or to anti-quark line 0 on both ends. This is all summed over. And now we have an S matrix here and an S matrix here because we have two independent dipoles. Remember, at the latency limit, another feature is different. All the diagrams are planar. Non-planar diagrams are suppressed by powers of NC. So these two dipoles don't talk to each other. In the next step of evolution, you cannot emit a gluon that starts in one dipole and goes into another one. That would be suppressed by powers of NC. So such crosstalk is not allowed. So your dipoles, after your dipole splits into two dipoles, the dipoles don't know about each other anymore. They interact completely independently with the target. So if you have this X1, this is X0, the gluon say was at X2, you have the S matrix here of X1 and X2. I'm going to suppress the energy dependence just to fit this. And here you have S matrix of X2 and that's X0. Okay. Now, yeah.
I think I'm just having trouble following like the color loops, I guess. Like in the diagram where you have a double quark anti-quark, it looks like that looks like a red anti-red, I guess. And then yeah. So, and then on the other side after, there's some kind of color rotation because that gluon isn't going to be an anti-red. It's a red, in this case, red anti-green or something like that. So in this bottom picture, it looks like X1 and X0 have to be opposite colors.
Okay, I'm not. I understood the issue. So we start out with quark being red, the anti-quark being red.
Yeah.
In the end, your quark blue, your anti-quark is anti-blue. That's fine, right? That's legit. It's the same thing for all of the diagrams. So what if this is red, this would be anti-red. If this is blue, this would be anti-blue.
Okay.
I mean, you can draw some other diagrams, you can move things around, but it would not be the original color.
Okay, thank you.
Okay. What I haven't talked about is there are also virtual diagrams. You can also have diagrams. Oh gosh. Maybe I should write something here. You can also have diagrams where you just have virtual corrections like this. Why? Because why not, right? Wherever we have real emissions, you always have virtual corrections as well. So you have to add the contribution of the virtual correction, which in this case, which really don't. So the virtual correction is just a little loop down here. It doesn't change the original dipole, X1 and 0. So your S matrix is still the same S matrix of X1 and X0. Okay. So that's a self-consistent evolution equation for the dipole S matrix, valid in the latency limit. The derivative of the original S matrix is equal to, you have to calculate this gluon emission to calculate the integral kernel. Then you have a term quadratic in S, and then you have a term linear in S. Okay. So in the end of the day, when we assemble it all together, I have to erase something, so I'm going to erase this stuff here. We get 3D log S over S matrix of X1, X naught, and say little s center of mass energy is equal to. Now, the calculation I'm not doing is the calculation of this gluon emission, right? You can do it in your favorite way. You can use light conway functions I alluded to yesterday, or you can just use Feynman diagrams and put gluon propagators here. Whatever rocks your boat, you can do the calculation. Then at this leading order equation C, you get alpha s and C over 2 pi squared integral. I'm going to explain the notation. You integrate over all the positions x2 of this gluon, right? That's an internal integration variable, has to be integrated out. Then you have x10 squared, x21 squared, x20 squared. I'll explain what these are. Then you have the term with two S matrices, x1, x2, s. S happens if you work on spin so long that every time you write the letter S, you put a vector over it. And the virtual correction, as you know, often happens to virtual corrections, like it comes with a minus sign. So if you calculate the virtual correction with negative, that's why there's a minus sign here. And you have the S matrix of x1, x1, x0, and little s. The explanation for the kernel, if you have xij, it's an absolute value of xi minus xj. It's a distance between positions of a quark and anti-quark lines in the transfer space. Just an abbreviated notation, not to write clunky absolute value things everywhere. So x10 is the size of the original parent dipole, x10, x21, and x20 are the sizes of these daughter dipoles, x21 and x20. So blue dipole and the red dipole in the original picture. Okay, great. So we have a nonlinear evolution equation. We can rewrite it in terms of the scattering amplitude n, right? This was done for the S matrix. And now we can switch to the dipole amplitude n. That's a very simple transition, right? N is just 1 minus S. So therefore, the equation becomes dv log S of n of x1 x0 little s equal to alpha s and c. So I'm just going to write the answer. If you want, that's a quick exercise for you to do to derive it. So you have several linear terms now, n of x1 and x2, n of x2 and x0. And then you have n of x1 and x0 coming from virtual term. And then you have a quadratic term, n of x1 and x2, and n of x2, x0, x. Okay. So this is a nonlinear evolution equation whose solution gives us the energy dependence of the dipole amplitude, right? Because it's a differential equation. And as the initial, well, you say, okay, you wrote a first order differential equation. What's the initial condition? The initial condition, we're going to require that at some initial energy S equal to S naught, we're going to recover that Glauber-Müller formula we have here. So if 1 minus e to the 1/4 x curve squared, I'm going to call this S naught, the initial saturation scale, squared in the exponent numbers. So this is the initial condition. The first three terms on the right here, if my interaction is weak and I can neglect the quadratic term, I only keep the linear terms, this will give me the well-known BFK equation. And together, this is a nonlinear evolution. So what do you think happens if I solve this equation? Would I violate unitarity? Would n become greater than 1? It seems like, right? I mean, we have a positive definite kernel, right? So as I increase energy, the kernel would try to increase my dipole amplitude. Could the dipole amplitude exceed 1 if I solve this equation? It's a bit of a difficult question. You stare at it for a while.
You have an n,
Huh?
you have an n squared there,
Okay, so
becomes dominant and comes to the one.
it doesn't become dominant, rather, well, if n becomes bigger than 1, it will be dominant. But
Yeah.
the answer is we don't get there. But you can see right away is when n approaches 1, you have n plus n minus n squared. If n is 1, you have 1 plus 1 minus 1 minus 1, the right-hand side goes to 0. So when you approach unitarity limit, you approach the black disk limit, right-hand side vanishes, and then your energy dependence dies off, right? Your energy derivative with respect to log of energy becomes 0, and your dipole amplitude stops growing. So if n approaches to 1, right-hand side goes to 0, therefore dn d log s goes to 0, therefore n just stays at 1. It doesn't exceed 1. If you wish, it's a fixed point of this evolution. Remember, in QFT, you have beta functions. Beta functions have fixed points. In other words, if beta function is 0, your coupling cannot pass that point, right? Your coupling asymptotically approaches that value of the coupling where beta function is 0, either in an IR or UV. There's something similar here. As you increase the energy, n tries to approach 1, but it's a fixed point of this evolution, so you don't violate unitarity. So since Alexei is suggestively looking at the plot, let me switch to the slideshow mode and yeah.
Is the evolution of the coupling taken into account here, or?
At this order, this is a leading order in this resummation parameter. So again, resummation parameters. The summation parameters are alpha s, since it's a legend C, alpha s and c log of energy, order 1. And we have this alpha s squared e to the 1/3 in the initial conditions, order 1. At this order, running coupling is high order corrections, strictly speaking. So the coupling here is fixed. That being said, the first correction people have calculated this evolution was a running coupling. Not just the proper NLO, which would be order alpha squared correction to the kernel, but only the running coupling part of it. And you know how you do running coupling. If you heard of the BLM scheme, you put port bubbles on all the blue lines and iterate them to orders. Well, anyway, you can kind of guess how the coupling runs from those type of calculations. Some people don't like them, and also for good reasons. But anyway, so in the end of the day, actually, it's quite complicated how the coupling runs with the sizes of the dipoles. It's so if you want to run the coupling, it will become a function of all 3 dipole sizes, right? You have the parent dipole and 2 daughter dipoles. You ask him what is the scale of the running coupling. Very, very ballpark answer. It runs with the smallest of the 3 distances. Smallest distance means highest moment. So it's as perturbative as it can be. So the coupling roughly runs with the smallest of 3 distances. The exact expression, though, is a lot more convoluted than the answer. Okay. All right. So let's just say we have a nonlinear evolution equation. Linear part is BFKL. Otherwise, it's fully nonlinear. How do we solve it? Well, really, there is no exact analytic solution of this equation. There is only there are approximate solutions and numerical solutions. This is all okay. If you want to go beyond legend C, by the way, there is a Jim-Walk equation, which is a functional differential equation, which is in my slides, but I have no time to discuss it. But if you're just solving this evolution equation, this is a numerical solution. This is the dipole amplitude n, plotted again as a function of the dipole size x perp, except now x perp is on a log scale. the dashed line is the initial condition, the GGM formula we derived earlier today. And then in this numerical solution by Javier Albacete, a couple of decades ago already, he just increases alpha SY gradually from 0 up. And you see the dashed line becomes the rightmost solid line. And as he increases rapidity Y, by the way, rapidity is like a log of energy. So I should write it somewhere in a different color. So Y is sort of like log of energy. If you're not familiar with rapidity, you can also think of it as log 1 over x. So large energy means small x, means high rapidity Y variable. So as he increases the energy, the curve keeps creeping to the left. So it means several things. One thing you can see is that the curve actually stays below 1, right? It approaches 1 asymptotically. We don't violate the black disk limit, unitarity is restored. The other thing you see is that the turnover point, turnover from growth to saturation, is 1 over saturation scale. And as rapidity increases, 1 over QS decreases, right? It moves to the left. That means the saturation scale is actually increasing with energy or with rapidity. And one can numerically show and analytically as well, the saturation scale grows as 1 over x to some power lambda. So as you go to higher energy or to smaller x, saturation scale grows and this dipole amplitude profile slides to the left. So this is the conclusion that saturation scale actually grows with a log of energy, say from this numerical solution. And okay, there's other nifty features which I have no time to describe, but essentially in terms of a big physical picture, what this means is that we kind of start with some sort of this is a very bird's eye view of everything we just discussed. Like forget all the technical details. You start with a proton or a nucleus, you go to lower x, you produce a lot more stuff, a lot more particles, and you create a denser system. And that's a saturated medium. Some people call it color glass condensate. In terms of maybe a more detailed picture, this is a log 1 over x, log q squared plane. You often see it in EIC talks in terms of kinematic coverage. So high energy or low x is up on this vertical axis. High q squared, short distances are to the right, longer transverse distances are to the left. What we see is as we go towards lower value of x, the system gets denser and denser, and we get this dense system of partons. But for smaller size partons, high density is reached later. So the transition into the saturation region is actually, the border is kind of like this. It happens at higher values of x, if we have larger distances, so lower q squared, and at higher q squared, the transition happens at lower values of x. So this is a transition. This is, if you wish, the saturation scale. And this is the picture you might have seen many times in various small x talks. This is indeed the saturation region. And this nonlinear evolution is what gets you there. BFK evolution gets you close to it, but it would violate unitarity. You need nonlinear corrections to restore unitarity for n to be less smaller than 1. And that's a transition to the saturation region. Now, I did not have the time to talk about geometric scaling, so let's leave it hanging. If you wish, you can ask me. We also discussed it last night quite a bit in the discussion session. Okay, this is the same plot, by the way, just x and q squared x is changed, but this is what you see in the EIC white paper. Okay, I have no time to discuss geometric scaling, so let's just give you a list of references. There was, over the years, a number of reviews has been written on the subject, and indeed, the book that you're all encouraged to read, and buying is optional, but please read if you're interested in the subject. So thank you very much. I think I'm just going to stop.
If we do not resum the second line, alpha is a to power 1,3, just resum the above, will we still preserve the unitarity?
Well, if we don't resum the second line, our initial condition would be not this formula, but its expansion to the linear order in this exponent, which would violate unitarity from the outset, right? So you would start with your initial conditions, which would kind of look like like this. Right, so you would violate unitarity from the get-go. Too late, you violated unitarity. Now, what's going to happen to the evolution equation if you feed these initial conditions into it? I'm actually not sure. Because it's not a physical initial condition. I don't think anyone has tried. It may be that in the end, like the question over there was stated, right, that very large and the quadratic term would dominate, and maybe it would drive it down. And it would kind of correct this unitarity violation, but I actually honestly don't know. I don't think anyone I've seen would do this again, because you don't want to put something on physical. But I guess out of mathematical curiosity, that's a valid question, right? Whether it's a stable fixed point, it's a stable fixed point for n less than 1, it would approach that fixed point. N greater than 1. I kind of think so. Actually, now that I'm thinking, maybe it might have been studies which would say try to correct itself. But it's kind of, again, it's not very physical. You already start with a violation like this limit. So it's too late. You already cut your head. But I think mathematically it's a stable fixed point. So as you present it, it will probably go down. But it's check. Yeah.
I was talking to Matt about something or other. I guess I don't remember exactly what. But he was saying something along the lines of BK solving what he called a little unitarity problem. But there's still a big unitarity problem. I don't remember exactly what the context was, but
well, okay, I don't know about big or little. So we certainly preserve the equation is written solves unitarity at a given input parameter. There's a big unitarity problem, maybe. Okay, so I'm going to erase something here. The question is, remember, in the end of the day, to calculate any cross-section involving hadrons or even the dipole, remember the dipole cross-section, it was integral over all input parameters of the dipole amplitude. Okay. So suppose you don't violate unitarity, n is bounded by 1. So this thing will be bounded by 2 pi r squared. Well, the question is, what is r? What is your radius? Right? I mean, my discussion there was very simple to convey the physics message, but once you think of real hadrons or real nuclei, right, you can think of a radius of a nucleus or radius of a proton. But that's not entirely true. You may have a collision where you miss the proton, but you still have some interaction between your dipole and the proton. So R is more like the interaction range. So interaction range. And the problem is that you can do an argument, and I think I showed it in a discussion yesterday, Heisenberg's argument, that if you have some sort of a peripheral collision with exchange of something at large input parameters, it must be some hadron or glue ball, as we discussed, then your scattering amplitude goes as s to the delta e to the minus m perturb. And if this scattering amplitude becomes order 1, that means your range perturb goes as 1 over m delta log of s. So it grows only logarithmic energy. So in other words, R is proportional to log of energy, and then your total cross section, which is bounded by 2 pi r squared, will be bounded by something which scales as log squared of energy, and this is known as a cross-R bound. So no hadronic cross-section at asymptotically high energies can grow faster than a log squared of energy. Okay. The problem is that for this argument to work, you have to have a massive particle. If we're doing perturbation theory, our particles are gluons, they are massless. Right? So here you need to now have a mass gap, you need to have scale in your theory like lambda QCD, bound state, so essentially confinement, right? Essentially non-perturbative input is needed to calculate the mass. So for gluons only, with glue only, the argument becomes s to the delta over 1 over b to some power line force, being of order 1, and then B grows as S to the delta over 4, and sigma total scales as S to the delta over 2. It grows as a power of energy violates the Frost-R bound. So if you only have blue ones, you cannot solve the Frost-R bound. You cannot satisfy the Frost-R bound because it involves non-perturbative long distance physics dominated by hadron exchanges. And yeah, I mean, but that's a very hard problem, right? I mean, it's literally, it seems to solve this problem, you have to solve the problem of confinement in QCD. So that's sort of not too shabby, right? Question. Yeah, so what this nonlinear evolution makes sure is that you're satisfying the black disk limit, right? This bound is the black disk limit, but it does not constrain the growth of the interaction range of the radius, typical radius of the interaction to be logarithmic. Well, you know, you win some, and there are some other battles.
Homework.
Yeah, homework, that's right. Homework.
Any other questions or comments?
Yeah.
This was initial condition. Well, what about boundary condition?
This is the initial condition. There is no boundary, so it's a linear differential equation. In principle, of course, you need all these dipole amplitudes to be defined everywhere in the transverse plane, right, for the integral to make sense. And you may argue that some distances are very long and non-perturbed. And the answer to that is that in the end of the day, the nonlinear saturation dynamics already in the initial condition, for instance, filters out very large dipoles, right? If the dipole is very large, n approaches 1 in the initial conditions, and that doesn't contribute much to the integrand because the integrand vanishes when n approaches 1. So you don't need boundary conditions beyond that. You should worry, of course, again, about large distances being non-perturbative, but that's why you need the saturation scale, because it screens out large distances, suppresses the contributions of very long distances. So you don't need boundary conditions, you only need the initial conditions. In a way, it's not dissimilar to, say, T-lab evolution in a Tim Hobbes talk, right? You have initial conditions of X, which are given at all values of X. And that's what you need. There's no boundary conditions. It's an evolution equation in Q squared, first order differential equation in Q squared. You only need the initial conditions at some Q equals to Q naught.
Yeah, sometimes people do like a matching with the BFKL.
Oh, matching with Diglap, yes. That's a different story, right? So yes, of course, you may start worrying that this resummation is of logs of energy or logs of 1 over x. Diglap is the resummation of logs of Q squared. How do we reconcile it? And that's maybe another homework problem for the crowd. There is a region. So if I take a large Q squared limit, which for us here corresponds to very small dipoles, subset of this parameter is alpha s log 1 over x is log of energy. And then you can get the log of Q squared. So this is known as a double log resummation. So you can, if I take the small dipole limit of this evolution equation, I'm going to recover an equation that resums powers of this parameter. And if I solve that equation, I get exactly the same result as if I take Diglap evolution and take a small x limit of Diglap. So this is a double log approximation, DLA, double log approximation, where both BFKL, so only the linear evolution here contributes in this limit, BFKL and Diglap evolutions overlap and give you the same result. Now, if you want to get ambitious and write an equation which goes and resums both logs of 1 over x and logs of Q squared separately, like small x evolution and Diglap evolution combined, well, many people have tried. It's really hard to do it rigorously. So no one has succeeded yet to write a single equation that does everything. So yeah, in the spirit of Alexis' suggestion, it's also another homework problem. Maybe a little bit more manageable than confinement.
For the last two papers, don't send me or Yuri, send them directly to journals or.
Well, no, send them to us. We'll send them to journals.
Let us thank Yuri for his lectures. We have lunch. Let's try to come back at 1:30.